Okay, perfect. Let's start. Uh, yeah, by the way, Lab 5 is out. The traditional Lab 5 is out. So if you want to give it a try, please go ahead and see if you can implement a file system in the LXOS. And as mentioned in the announcement, the grade will be adjusted, so you cannot do lab 5 and you cannot skip, for instance, final. So the lab 5, like the lab score will be capped at 65%. So doing lab 5, like the regular lab 5, doesn't allow you to be exempted from midterm or final. Okay. So today we'll look into Linux storage stack. The reason why we chose Linux is because it's open source, and I like Linux and I'm more comfortable with Linux. And the second most important thing is like the storage stack of Linux is so well designed that most of it, like foundations, come because of like the way it is designed. Because in Linux everything is a file, so there is a lot of thought that went into the design of Linux storage stack. So how does it look? So it's very modular and layered. So here we have syscall interface at the top. Okay. So any file that you want to access is through system calls like open, read, write, stat, so on and so forth. There are various system calls. And then under the system call, there is virtual file system. Okay. Then under the virtual file systems, there are actual file systems uh, that you as a user should implement. For instance, ext4 would be a file system, and FAT32 is also a file system, so on and so forth. Okay, and file systems, most of the file systems, they operate on blocks. So there is a common component called block scheduler that takes care of handling disk blocks or device blocks. Okay, so this provides a general abstraction for all the devices that operate at block level, okay, where the access, basically the reads and writes, happen at the granularity of block. So to handle those devices, block scheduler provides a uniform interface. And then we have device drivers that actually know how to talk to the actual devices. For instance, SCSI is a device interface. So in order to talk to, for instance, Samsung SSD, you need to follow certain protocols, certain commands. And maybe in order to communicate with, for instance, uh, like SanDisk, hard disk, you may need to send certain commands. Okay, so those things will be taken care by the device drivers, and these will be written by the device manufacturers themselves. Okay, so like for instance, like Samsung will be written by the Samsung, and SanDisk will be written by the SanDisk developers. Okay? And they don't worry about like file system. Okay, so SanDisk developer, for instance, or like the manufacturers who produce this hard disk, magnetic disks, they don't care about the file systems. They just write the device drivers that allows you to communicate with the disk. That's it. They don't worry about like whether the file system is ext3, FAT32. No. And then at the bottom we have hardware devices. These are the actual devices that we interact with. Okay. So note that the file system developers has to do very minimal, like they are independent from the device on which the file system is located. Okay. Irrespective of whether the file system is on the USB drive or on SSD or magnetic disk or tape, the file system remains the same. File system is agnostic to the storage that is used to store that particular file system. At the same time, device is also unaware, or like device doesn't care about the type of file system that is stored on it. And this interface is like, this is bridged by like VFS and the block scheduler. So for, yeah, file system just takes care of mapping like inode numbers to blocks. And block scheduler takes care of mapping blocks, like the actual blocks, to the blocks of the device. And then device drivers actually takes care of like transferring this block into the hardware device. And VFS, like virtual file system, it only deals with inodes. So it doesn't care about what file system the underlying inode is. VFS only wants, hey, okay, hey, give me the inode for this file, that's it. And file system actually does all the path traversal and everything, and it will give the inode number. And how to get the inode number, that will be taken care by the file system. VFS doesn't care about that. Okay. And yeah, so there are like 42 file systems that are supported in Linux. So if you like, have you looked at file systems on like ECN Grid, for instance? Anybody? So let's have a look at the file systems. Okay, so this is, I logged into EC Grid. So here, so these are all like the file systems that are mounted at different location, different paths. And you can use -T to get the file system that is mounted. Okay, so here tempfs, it's the tempfs file system. There is xfs and there is nfs. So you see all the file systems are different. However, for users, like when we write our applications, we don't care about file systems. All we do is we just use syscalls, right? We just do open, read, write, and we give the path where the file is located. We just use the same system calls to read and write, irrespective of the file system that is supporting the corresponding file. Okay. So here there are like tempfs. At least I can count 4 file systems here. So in Linux there are like at least 42 file systems that are supported. And it also provides, and this is one of the main reason of the abstraction in Linux, where everything is a file. If you want to communicate with the Linux kernel, again, you can communicate that through file operations. And Linux kernel can communicate to you, to user space, through file by exposing a file. Okay. So for applications, they don't worry about the underlying file system. They just use syscalls, which will be translated by the VFS layer. For file system implementers, they need to take care of mapping the inode numbers to the disk blocks, okay, to the block, to rather to the blocks. Okay, not exactly the disk blocks, but rather to certain block numbers. Okay. So this is what file system implementers do. They just take care of translating inode numbers, which virtual file system works with, to the block numbers or block offsets, which will be taken by the block scheduler. Okay. So before going into page cache, we can actually look at few interesting things. Like, so okay, so okay, these are okay. Page cache. Yeah, let's look at page cache. Are there any questions with respect to virtual file system or like anything? Any questions up to this point? Okay. I see that much. So one of the important and rather a very interesting thing about Linux storage stack is page cache. Okay, so Linux uses page cache to avoid disk I/O. To avoid frequent disk I/O, it uses page cache. Basically, these are pages maintained by kernel for storing contents that uh, that that go to or from the disk. Okay, So here you can imagine that each block will be mapped to a page in main memory. Okay. So this allows Linux to uh, like accumulate all the writes that happen to a file before doing the actual disk IO. For instance, like imagine if you write a simple program, and when you write a single character to a file, and if Linux, if operating system has to send a disk request for each byte that you write, good luck, because the request to a disk itself will be like 4 bytes, and then the data that it is sending is just 1 byte, and there's too much overhead, right? So page cache allows Linux kernel to accumulate all the writes that happen to a specific disk block, and then once, mm, like at certain points, or when the page is needed, or like when the process terminates, so it can actually uh, flush the things, or like flush the modified contents of the page in the page cache to the corresponding disk block. So yeah, when like when we do syscalls, like read write syscalls, those requests will be served from the page cache. So when we actually read, for instance, read some file, the read happens by looking at the by looking at the corresponding page in the page cache, not exactly by reading the corresponding disk block from the file. So what happens is when we read, Linux kernel takes the disk block from the disk to the page cache and then serves all the read requests from the page cache. And it also allows Linux to read all the pages for a file ahead of time before even process requesting. That's why you get this feeling that, so whenever you are accessing, if you notice, right, let's say when you are reading or writing a file, you see that at page intervals, like try to read a file which is very large, let's say, which is let's 10 MB, okay? When you try to read a file, you'll notice that the delay that happens when you try to read, like, memory will be high at the page boundaries. Okay, it'll be constant, like it'll be high at the page boundaries because it needs to get the page from the it needs to get the page from the disk to the page cache, and then like if the read happens to the memory which is in page cache, then the speed will be too high, right? Like, I mean, it's as if you are doing memory reads. So similarly, writes uh, happens through to the page cache, and when you do a write, the corresponding page in the page cache will be marked as dirty, and then the dirty pages will be written back to the disk block later. And this can make certain data to be lost, especially when a process has written some data, but let's say process crashes or something happens to the disk, then you cannot be sure that the writes that you made are actually written to the file. Have you ever noticed this thing? And also, especially like when you are when you have, if you have written some program that prints some commands to the console, you might have noticed it that few times the print statements won't get printed until you have a new line, or if you do f flush or something. Have you ever used a flush, especially like when you're communicating with console, like flush std out or like flush one, these commands in your programs? Can you guys hear me? Hello? Okay. So, okay. So have you guys used flush anytime in like in writing C programs? Have you guys done flush? Is anyone aware of flush? Oh, okay. Yeah. Few students, I think Michael says yes. Yeah. Okay. Nicholas says yes. Exactly. So Yeah, flush is one way to say to tell operating system to like write all the data which in the page cache to the actual device. That's why when you do flush on std out is also a file, right? So the writes will happen to the page cache. So when you do flush, that is when it actually the data will be written to the device. Device in this case is console, that is your monitor. So that's why when you do flush, you can be sure that the all the print statements that you have done or like the data that you have printed to the console will appear onto the console. So this is Linux kernel also provides a system call to do flushes, which is called sync. When you do sync, you can be sure you can be sure that all the writes are flush, or rather all the writes are committed to the corresponding file. Okay, so yeah, so in presence of page cache, as I mentioned, all the reads or writes will be served from the page cache. So when you do read, like read syscall, and with the corresponding file descriptor and offset, so read actually sees if if there is a page cache, like if the page is present, if the corresponding the corresponding disk block is present in the page cache. If not, then the corresponding disk block will be fetched from the disk and put it into the page cache, and then the request will be served from the page cache. Okay. So, and for each node, like the way page cache is implemented is for each file, there is an address space. So for each file has its own pages, right? Its own page cache. Okay. So each file, basically the inode and the corresponding file offset will be mapped to a page in page cache. So there is a map from inode number and file offset to the page. Okay, that is how page caches will be maintained, and mostly it uses radix tree. You can see in few kernel implementations you could see red black tree as well, but radix tree is the commonly used data structure to store page cache map. Okay. And also for each page in the page cache, uh, Linux kernel also stores the reference to the corresponding file to which the page belongs, and also process which has access to that particular page. And it also stores the offset within the corresponding file which the page belongs to. So yeah, let's look at a few interesting things about page cache. Okay. Cat proc meminfo. So this is a command, like, so meminfo is a file that you can read, proc meminfo, that gives you all the memory, like memory usage of the operating system. Okay. So it is saying that total physical memory is 16 GB, and the free memory is 6 GB, and like the memory that I can use is 10 GB. Total memory that I can use is 10 GB. This is including the swap space, right? And then there is all the different memory pools that it maintains. So this is the stats of all the memory pools. That's why, like, have you guys ever used free? You must have seen like uh, free is a command that you generally use to look for memory. You must have used this free command. Uh, like when checking for some memory, you must have heard of this free command, right? So if we use the same trick, like if you use strace of free, you will see that it's actually, it just reads from proc info. You see this thing? So what free is doing is it just reading the proc info and displaying it in a nice format. That's it. So you can actually do it yourself by reading the meminfo. So, and you can actually see what, like the status of page cache by looking at dirty pages in meminfo. So dirty pages are 8 KB. So there are two pages which are dirty. That means there are two pages uh, in the page cache which we have written to, but they have not synced onto the actual device. Okay. So if you see, this thing stays the same. However, the sync is a command. So sync is a program that synchronizes all the writes, cached writes to the persistent storage. So if you do sync, you can be sure that all the writes that happen will be flushed onto the disk. You see, now the dirty or like the pages that are not written or rather dirty in the page cache is 0. So sync will ensure that all the pages are written. Now let's see. Okay, it's dirty. So, but now let's say if I open some browser, if I do something, and now let's see the, okay, you see now the dirty, there are many dirty pages, right? So now you can do sync, perfect, you see? So sync is a command that can force Linux kernel to flush all the pages in the page cache to the actual persistent storage. And other thing, yeah, before looking at mmap system call, we can actually look into two things. I'm just thinking, okay, maybe after mmap, we can, like, after looking at mmap system call, we can look at process memory and see how, like how the program gets mapped into the memory and what are the system calls used by Linux to map program memory to the actual like virtual memory of the process. So did anybody like, is anyone aware of mmap system call, or like did anybody used mmap system call before? Okay, I take that answer as no. So mmap is a system call which allows you to map blocks of the file, like blocks of certain file to your virtual address space. Okay. So for mmap, the syntax of mmap is the address. First argument is the address where you want to map. This is the virtual address within the process address space where we want to map. And then the length of the map. Okay. Length is usually lower bound of the length is 1 page, at least a page. Of course, you can provide arbitrary length, but it will be rounded off to the nearest page. Okay. And then protocol is the permissions. Basically the permissions, like prot is not protocol, it's protection. So it could be read, write, executable. Okay. So these are the permission bits, how we want to map the memory. And flags is again like, for instance, map private makes a copy on write mapping, map shared makes a shared mapping. That way these maps, these virtual addresses or like the mappings are shared between all the processes. Okay. Or like when you clone, the map will be shared. And then there is map shared validate, which is in the latest Linux versions, which is similar to map shared, but it has certain like different behaviors, especially when the file is not backed up, when the file descriptor is not backed up by a block file. Then offset is offset within the file. Perfect. So this is the mmap call where, like, if you pass null as the first parameter, then Linux kernel will pick any virtual address which is free, which is available within the process address space, and it will return that particular virtual address. Okay. So mmap, we do mmap here. What we are saying is, so at offset 0, we are telling Linux kernel to map the first block that starts at offset 0 and return the starting address of that particular page. Okay. And then here now, once we do mmap, we don't need to use read, write system calls anymore. We can just read the file as if we are reading the memory. Okay, so here the first block of the file is mapped to the first page whose address is in data. Okay, now reading seventh character from a file is just indexing the array data. Similarly, writing is just writing to a memory. That's it. So mmap allows us to do bypass all the reads and writes and to like use memory read and write as file reads and writes. Okay, and mmap also allows us to do serialization. Like, have you guys aware of like serialization, deserialization? If you have used Python, it's called pickling. Have you guys heard of these terms? Serialization, JSON serialization, Java serialization. Yeah, exactly. So serialization, this is perfect way to deserialize an object which is in a file. Because if you want to deserialize, you don't need to read through all the fields one by one. You just mmap the serialized file. And once you mmap, you just cast, for instance, let's say the first structure at offset 0 is certain program structure. Now you can just cast the data to the pointer of corresponding structure. That way uh, you can access data within the file using your own structure. See, is this same stream streaming a buffer uh, in Java? Sure, yes, yes, yeah, it's implemented in the same way, yes. Yeah. So, I mean, a C in and C out, those ideally those depend on the C++ standard. Those could be using mmaps, or they could be doing direct read and write system calls themselves. Okay, but my gut feeling is that they would be using mmaps. Okay, and similar to sync, there is also msync that allows processes to sync, or like rather flush all the writes made by uh, mmap, or like, yeah, made by mmap to the corresponding file. Like, this is the same, like uh, same counterpart as sync, but this is for mmap, this for mmap region. Now for when we have page cache, sorry, when we have mmap, now read and writes are very easy. So when we do mmap, the flow is still the same. We first see page cache. If the page is not available, we get the corresponding page from the disk. We put it in page cache, and then the mapping is established between the user virtual address and the page cache. So basically, page cache, like the user virtual address, it maps to the same page that is pointed by the page cache of that corresponding disk block. So mmap provides amazing advantages, right? No system calls on each access. Once you do mmap, every reads and writes to file is just regular reads and writes, and the flow of data is just from the page cache to the disk. That's it. Okay. And however, we may have to create extra page table entries, because now there are two page table entries, right? One, there is an entry in page cache, and there is also an entry in the process virtual address space, where both of them, they point to the same physical block, or like same physical page. And mmap could be hard or like tricky when we have large files, and when there are input output errors, then mmap might fail, or you may need to uh, do some defensive programming, especially when you map a block to your memory, and let's say that particular disk block fails because of some error in the disk. So in that case, although you think that mmap, like writing to that memory, has has been successful, that may not always be the case. Uh, Regular IO, this is universal. Now you don't need to worry about existence of mmap. By the way, mmap may not be supported by all the file systems, okay, or like all the devices in few cases. And file IO is a regular file IO. You can do read and write, the same traditional input output. Here, the one problem is when you are doing frequent reads and writes, the data flow is, there is overhead in the data flow, because now the data has to go from user space buffer to the kernel space buffer, okay? And then from the kernel space buffer to the page cache, and then from page cache to disk. Whereas in case of mmap, it's just directly from page cache to the disk block, because uh, application will be writing directly to the page of that disk block. Okay. Now let's look at a process. For instance, okay, let's look few examples of mmap. Okay. So this is a simple mmap example. So here, what I'm doing is I'm mapping mmap hello file. I'm opening mmap hello file. I'm opening with read write permissions, and then mapping the first 1000 bytes, like 1 kilobytes from offset 0, and asking kernel to give some memory, some free virtual address which is in my address space. Okay, and then I'm writing h and e to a map hello file. Okay, and then I just print something. I just do like I just wait for the user to press some program. Now let's see what happens. Well, let me create 0 output file. Hello. Let me create a file of 16 KB. Okay, perfect. I did create a file of 16 KB. Let's see what the file contains. Okay, as you can see, the file contains all zeros. Okay, hello, the file contains all zeros. Okay, now let's compile mmap. Okay, it says check file. Let me check the file. Looks like it did not write, but I mean, this could be because the writes could be in page cache. So let's finish it. Okay, let's see. Wow, it did not write. Wait a second. Let me open the thing again. Oh, wow, it did not write. Okay, what did we do wrong here? Let's see. Okay, I see. Okay, can you guys tell me what is the thing what wrong, like what is the error in this program? Yeah, let's take step by step. Okay, so so this is the program that we have. Okay, at the top. Let me exit this guy. Okay, let's look at a few flags of mmap. Okay, first address could be null. If address is null, then kernel chooses the address to which create mapping. Very nice. What is the second? Second field is length. Uh, where is the length? The address is chosen. Okay, the length argument specifies the length of the mapping. Oh, okay. With this is no right access. No, I do have right access, right? Because I'm mapping read write. I'm mapping the file to read write, and I'm like I just wrote these two. If there was no right access, I think it would like it would fault. I would do segfault. Yeah, that's a good question. We can actually try what happens if I try to write a page that I have marked read only, and also I gave it right here. Might have to close, but I think it should. Uh, no, that's not true because I think when I exit the program, all the files will be closed, right? Don't you think so? Like all the files that are opened by me should close. So okay, now let's look at proto write. Protection write page may be written. Very nice. Now let's look. Okay, let's look at map write, map private. Okay. So what does this map private do? Okay. Ah. You see, it creates a read-only copy on write mapping. So when I actually write, it doesn't actually write to the file. It just creates a new copy. You see, updates to the mapping are not visible to other process mappings to the same file and are not carried through the underlying file. So map shade is the flag that I need because visible to the other process of the same region, and in the file backend mappings are carried through to the underlying file. Okay, let's use map shared. Okay. Let's see the file before running our program. Okay, it's all zeros. Okay, let me check file now. You see? So yeah, map shared is the culprit. Okay, so perfect. So okay, again, like good question was what happens like when let's say we do this thing. Okay, I I I open the file read only. Okay. I open the file read only and I map the corresponding file read write right and see what happens. Okay. Oh, okay. Vidush, does that answer your question? Because I think the problem happens in mmap when you have read-only access and you try to do it. Okay. And I think you'll get the same thing. Okay, the problem happens here. So here, let's, the reason for mmap fails here. Oh, but it doesn't even. Wow, where does it? I don't know why it gets default, right? Where? Hmm. I put the key final symbols and just do run. Ah, okay. So it's here. So when I'm all like mmap succeeds, no. The thing is like mmap did succeed. Okay, mmap did not return null, but the page was mapped read only. So if we look at okay, so I think what's happening is here when we are trying to write to buff, we get segmentation fault. Okay, the thing is, so this is where we are getting segmentation fault. So if you see the content of RAX, so RAX is -1. Ah, okay. Actually, mmap exactly. I think mmap return -1 is mmap. Yeah, mmap return -1. Okay, let's see what mmap returns actually. Mmap, the return value. Ah, okay. With this, does this answer your question? On error, map failed is written, that is -1, and error number is set accordingly. So the way we need to fix this is yeah, perfect. Okay, so another thing we can look at is maps. So if you see the maps, okay, so these are all like pages that are backed by the file. So what the first entry, what it is saying is this is the virtual address of the process. The self is I'm just uh, we are looking at the maps of the cat program. Okay, so here this is a virtual address, and this is the offset within the file. Okay, and of this size from this offset, which is I think 2 pages. Yeah, which is 2 pages. As you can see, 8 KB, 2 pages starting from offset 0 is mapped read only. And P indicates a copy on write. So that means if this process, for instance, if cat tries to write to this memory, the writes will not happen to the file because that will be made, it's a copy on write mapping. So any writes made by the process will be done to a private copy and the writes will not be carried over to a file. Similarly, the next entry, this is a virtual address of the process and it is mapped as read executable, and this is offset within the file, and this is like major number and minor number, this is for devices, and this is the inode number. So if you do for instance, okay, so you see the inode number of cat, okay, that's exactly this. Okay, so the this is the like map, like virtual address map of cat, the program that we just ran. So here we are saying that the file, the cat file, the different sections of the binary, which is cat, are mapped to these virtual address regions. And these are the offsets within that file where the mapping happens. And these are the permissions of this corresponding virtual address regions. Similarly, we map libc into corresponding virtual address, and ld, the loader, into corresponding virtual address. Here, when the mapping doesn't have any file backing, so you can see that there is no major or minor number, and there is no inode number, and there is no offset because there is no file. These are, they don't have any backing storage. So all the writes that are made to these particular regions will not go to the disk. They'll still be stored onto the page cache, but then they will not go to the disk, but rather they will go to swap space when you need to swap the page, swap the process in and out of memory, because swap space is also a disk write. Okay. Uh, yeah. So we can. So any questions with page cache or anything in general, like with respect to file or memory mappings? That's why, by the way, try to like you can do all sorts of experiments with memmap, like mmap. For instance, like you can write your own program, okay, and try to map your own code segment into uh, read write, okay, read write region, or like rather you can actually change the permissions of your of the code page, okay. Like you can create, for instance, mprotect is a system call which allows you to change the protection bits of corresponding virtual address space. For instance, let's say if you want to write an executable, like write a read-only page, you can call mprotect, because at the end of the day, process has all the control of its own virtual address space, right? So what process can do is it can call mprotect and change the permission bits of pages and try to write to certain pages. Okay, that way, if a process really wants, for instance, you can see that if you're like if you have written some C programs, if you ever try to write to some constant variable, you may get some segmentation fault. Okay, and then you will realize that, oh, it's a constant. Oh, I'm trying to access it through some pointers. But let's say you really want to write to constant because of some reason, then you need to change the permission bits on that particular virtual address page. You can do that by using mprotect. So, like if you think deeply, you can use mprotect to write self-modifying code, right? So you can write a program that actually modifies itself while executing. Uh, that way, you cannot actually analyze the behavior statically. That means, like when you look at the code, it looks like something, but when you actually execute it, it does something completely different because uh, it can overwrite its own executable memory by like using mprotect to change the permission bits. This is the technique most of the malwares uses, by the way. So if you have like worked with malwares or viruses, the way they do is they first read certain encrypted data, and then they decrypt it, and they do mmap to map the data from a file into memory and mark that memory region executable, and they start executing the code. Okay, so when you look at the malware without actually running it, it looks all good. It doesn't do anything. However, when you run it, it does all the bad stuff. The reason for it is it uses these uh, memory protection mechanisms to uh, to generate executable code. Uh, any questions? Okay, yeah, if there are no questions, I think that's the end of the class. Thank you.
Oh, hey, Professor.
Hey,
Yeah, I also had to talk to you about the project. So I don't know if Professor Millen conveyed this to you, but I think he told me that you required someone to look into LLVM, right?
oh yeah,